All right, so thanks for coming. I'm talking today about what it says on the screen using matrices to count. Okay, so what does that mean? I guess like a couple things, but the general plan is we're gonna have a couple interesting, like pretty basic counting problems, and we're gonna use basic matrix arithmetic and linear algebra tools to solve them. So first example, that was supposed to advance the slide. First example, we're going to find a closed form for the Fibonacci numbers. So maybe you've seen this before, in which case this is very boring. Maybe you've seen this before, but presented without matrices, in which case this might be a little more interesting. Or maybe you haven't seen this at all, in which case it'll be shocking and a wonderful surprise. So the Fibonacci numbers are defined like this. You have the 0th Fibonacci number is 0, the next Fibonacci number is 1, and then to get the next Fibonacci number after that, you add the previous 2, and you keep doing that. You always add the previous 2 numbers to get the next Fibonacci number. So it would go 0, 1, 1, 2, 3, etc. All right. So the idea for us is going to be to study this function that takes a pair of consecutive Fibonacci numbers and then gives us back the next consecutive pair of Fibonacci numbers. The reason we want to study this function, I don't want to motivate it too much. We could get into a whole discussion about why you would think to do this. But just something to notice is this function might be interesting because it's easy to define the output in terms of the input, right? If I want to compute fn plus 1, I just have to know fn plus 1, that was in the input. And if I want to know fn plus 2, I can also compute that from the input. It's fn plus 1 and fn added together. So it's easy to write down a formula for this function. And also, I can iterate this function. I can take this function and I can apply the function to the output of the function and keep going to keep getting bigger and bigger terms of the Fibonacci sequence. Okay, so there are maybe 2 nice properties of this function. And another nice property of this function is that it's linear. So I guess the way I've written it, it takes like 2 consecutive Fibonacci numbers and returns the next 2 consecutive Fibonacci numbers. But there's a nice way to extend this function to all pairs of real numbers, where we just take 2 real numbers, a and b, and I return b comma a plus b. So I'm just taking, it does exactly this thing if my inputs happened to be 2 consecutive Fibonacci numbers. But if they were other numbers, then it'll give us something else. And so, as you might have guessed, this map is linear. It corresponds to some 2 by 2 matrix over the real line, over the real numbers. So here's that matrix. And I've just rewritten the same thing I said before. If I apply this to a vector AB, I get B and A plus B. All right. So let's call that matrix A, this matrix that increments the Fibonacci sequence for us. And just to make it clear, if I apply this matrix A to F0, F1, the first 2 Fibonacci numbers, I'm going to get the next 2 Fibonacci numbers. Well, the F1 and F2, like incrementing them both by 1. And if I apply it twice, well, that's just the same as applying A to the output of the previous thing, and that'll be F2, F3. And I could apply it again and again and again. And so if I apply A n times to our initial starting point of F0 equals 0 and F1 equals 1, I'm going to get Fn and Fn plus 1, those 2. Okay, so I guess something to notice is this A is a very explicit matrix, and that means A to the n is just a very explicit matrix of some entries in there, and I can just perform this matrix multiplication, and I'll get the Fibonacci numbers. So that seems like we're on the road to a closed form. The issue is just that we don't know what A to the n looks like. The entries of A to the n are definitely going to be something in particular, but how do we find a closed form for those entries? So that's the question I'd like to pose to the audience, if anyone has a plan. Any thoughts? What's some linear algebra tool we could apply? Sorry, yeah.
Can you just diagonalize it? And then
that's
power and then
the exact word I was looking for. Thank you. Right, so we're gonna try to diagonalize this matrix. Reason being, diagonal matrices are easy to take powers of, and diagonalized matrices are also easy. So yeah, in case it's been a long time since you took linear algebra, when you diagonalize a matrix, you write it as a product of some invertible matrix P times a diagonal matrix D times the inverse of that matrix P. That's what it means to diagonalize. And in this case, I've done it for us. I just took the matrix A, and I don't know, this is a standard procedure for doing this. And I came up with these matrices, P and D. In the matrix D, the diagonal entries are these numbers phi plus and phi minus, which are the roots of a particular quadratic polynomial, the characteristic polynomial of the matrix. And they happen to be 1 plus or minus root 5 over 2. So that's the plus and the minus. The positive root there, the 1 plus root 5 over 2, that's the golden ratio. And the other one is something else. Okay. So the golden ratio will be important in a sec. But now that we have this really explicit decomposition of A, it'll be easy to take powers of A. So just for context, here's our equation that we had, and the matrices P and D, and our roots phi plus minus. And what we know from before is that if I want this pair of like the nth Fibonacci number and the n plus first Fibonacci number, all I have to do is apply a n times to this initial vector 0, 1. And when I do that, that's the same as applying PD P inverse n times. So how does that work? Like, hopefully this is clear, but I do want to go through in more detail. So the idea is if I did like PD P inverse twice, what I would get is PD P inverse PD P inverse, and then the P and P inverse in the middle would cancel. So let me write that out. Oh, what's that? Sliding around all over the place. Gosh, how's that? Okay. So that would be like PD P inverse, PD P inverse, and these are going to cancel off, and I'll be left with P D squared P inverse, and etc. However many factors I had. So PD P inverse to the n is just P times D to the n times P inverse, and then we apply that to 0, 1. And since we have our, I have the matrix P and the matrix D computed, this is just like a really explicit computation. Also, D to the n is easy to compute because the powers of a diagonal matrix are given by just raising each entry in the diagonal matrix to that given power. So I went and computed P inverse for you and plugged in 0, 1, and I got this output 1 over root 5, negative 1 over root 5. And then I just have to take that and multiply it by D to the n, which is easy to do. I'm just going to multiply the 2 rows of that column vector. And what we're left with is that this pair, the n Fibonacci number and the n plus first Fibonacci number, is just the product of these three matrices. So this one was P, that one was D to the n, and that's P inverse applied to 0, 1. Okay, so there that is again. And we'll just expand this out. And remember, like, I guess in the end, I'm only interested in what's the nth Fibonacci number. So if I want to find that thing, I just need the first entry of this resulting matrix product, which I can write like this. You just go and do the matrix multiplication, and you expand everything out, and you get this explicit formula for the nth Fibonacci number. Okay, right, so either that was cool or boring. But this is, I guess, the setup for a more general concept that we'll talk about soon, which will let us solve some more interesting problems. All right. If you have any questions at any time, please feel free to interrupt me. I'm not watching any of your screens, so I won't know unless you say something. Okay. All right, so let's go over this approach that we used for this linear recurrence relation. This would work just fine for any other linear recurrence relation at all. It didn't have to be the Fibonacci numbers. And our procedure was you take the linear recurrence relation, you write down some matrix which implements this incrementation idea, where you want to have a bunch of consecutive entries in the sequence and then produce the next set of consecutive entries in the sequence. And there will always be some matrix that does this. If it's like a fourth order linear recurrence relation, it's going to be a 4 by 4 matrix. In our case, it was a second order linear recurrence relation, so we had a 2 by 2 matrix. But for any linear recurrence relation, this will always be possible to do. And the next step is to diagonalize, which I'll maybe say something about in a sec. And then once we diagonalize, we take the powers, we do the explicit matrix arithmetic, and we end up with some closed form answer for the general term of the sequence. So that's a very powerful technique. But of course, the issue is, what if we couldn't diagonalize it? Not every matrix is diagonalizable. So it would be a bummer if we ended up writing down this matrix and we couldn't diagonalize it, and then we're just kind of stuck. So I guess there's a few things I can say there. One thing is, if you only care about specific terms in the sequence, maybe you only care about the 1/1,000,000th term in particular. Then you could just write down the matrix, don't need to diagonalize it, just have a computer take a really big power of that matrix, which there are efficient algorithms to do. And once you've taken a really big power of the matrix, you just plug in your initial conditions and you get the answer for the 1/1,000,000th term in particular. So if you just need to find a particular term of the sequence, you can have a computer do it for you without diagonalizing. And another thing is, even if you can't diagonalize, there is always at least a Jordan canonical form, as long as you're working over some algebraically closed field. Or even if you're not working over an algebraically closed field, you can solve the recurrence relation over the algebraically closed field, and the answer will agree in the underlying field. So yeah, I guess those are technical issues. But the other thing is, almost every matrix is diagonalizable. This is rarely an issue. To be precise, that if you pick a random matrix, the odds are 100% that you're going to pick a diagonalizable one. And it's possible to pick a non-diagonalizable matrix, but it's just exceedingly rare. So probably in any recurrence relation you're going to solve, you'll be fine. All right. So now let's like generalize this technique to solve other problems. The idea of what we did here was we took our sequence and we found a matrix that incremented the stuff, and that's a useful and nice thing to do. But if we want to solve more complicated problems, we're not always going to have recurrence relations for our sequences. So we're going to try to solve counting problems where we're still trying to find the general form of an entry in some sequence. But now there's no easy linear recurrence relation for that sequence. And instead, what we're going to do is take our sequence and split it up as a sum of what I'm going to call baby sequences. I don't know what the right word is. And then we're going to split it up in a clever way so that these baby sequences have nice first order linear recurrence relations in terms of each other. So if this doesn't make sense yet, don't worry, we'll go and do examples. And then we do kind of the same thing. Once we have all these like baby sequences that we split up into, we find a matrix that increments all these baby sequences, and then we diagonalize that matrix, and then we do some explicit matrix computations, and we get a closed form for the answer. And so again, there's like a diagonalizability concern. Maybe our matrix wasn't diagonalizable, but matrices probably are diagonalizable when you encounter them. So it's rarely an issue. Okay. All right, so here's this like dynamic programming approach. That's the computer science term for this technique, is dynamic programming. So let's do this dynamic programming approach for our previous linear recurrence relation problem, and then we'll try a different counting problem. Okay, so the idea here is the papa sequence that I want to analyze is this f sub n plus 2. I'm writing this thing as a sum of these like baby sequences is the way I'm going to think about it. And so to do that, I'm going to define this like shifted version, sigma for shift. Sigma f is going to be the sequence that's just a shifted version of the Fibonacci numbers. The nth term of sigma f is the n plus first term of the Fibonacci numbers. Easy enough. And that just makes it easy to rewrite the equation like this. Here, sigma squared f means like a very similar thing, just shift twice. So the advantage of writing the equation in this way is that all the indices, is that all the indices over here are n. So there's no, all these things are n. So what I've really done is written this sequence sigma squared f as a sum of f and sigma f with all the same indices. Like in other words, this is really a sum in the vector space of sequences, if you like. And I now have, for these baby things, a recurrence relation for each one that's first order in terms of the other baby things. So I have fn plus 1 written as the nth term of sigma f, and I have sigma f n plus 1 being written as the nth term of f and the nth term of sigma f added together. So this is just another way to rewrite the recurrence relation for the Fibonacci numbers, but now all our recurrence relations are first order. And this is like really secretly the exact same thing we already did, but just like rephrased in this dynamic programming style. So you end up with like, you write down the same matrix, it implements the same operation. This is fn, and this is still fn plus 1, just written in a different way. And this is fn plus 1, and that's still fn plus 2, just written in a different way. But now this is like, I don't know, in the framework of dynamic programming, where we took this sequence we wanted to understand, and we wrote it as a sum of these two smaller things, and each of those satisfied some recurrence relations in terms of the others. Okay, so now let's do an actual interesting counting problem. No longer will we have a nice recurrence relation, and it's going to be some other complicated mess that we're going to solve with dynamic programming. So what is the counting problem here? I haven't described it at all, nor have I explained what's on this slide. So, okay, I'm going to consider a function from r to the n plus 1 to r to the n minus 1, I guess in this case, due to my indices. And what this function does is it takes a list of inputs. Like in this case, I drew the case where n equals 6 from x0 to x7. And the output is going to have 5 outputs in this case. No, sorry, 6 outputs in this case? Yeah. Where each output returns the maximum of the 3 inputs above it, if that makes sense. So like pictorially, that's what's happening here, is that I have 6 outputs. Each one can see 3 different inputs, and its output, the output of this coordinate here is always the maximum of these 3 inputs that it can see. So this is a thing you actually encounter in, for example, machine learning. This is like an example of a max pool layer, although like a really silly example. But you can do something similar for like actual machine learning things that occur in practice. And something to notice is that this function is piecewise linear. So like in a really simple case, if I just had 3 inputs going to 1 output, this is just like the max function. And that function is piecewise linear. In some parts of the domain, the first thing is the biggest, and then the output is just that first thing. And in some parts of the domain, the second thing is the biggest, and the output's the second thing. And in some parts of the domain, the third thing is the biggest, and the output is the third thing. In each of those pieces, it's linear. It's just one of the variables. But we have these different pieces. So the counting question we're going to answer is, how many pieces do we need to describe this piecewise function? Okay. So I'm going to describe kind of the, here are some of them. So one piece might be where x0 is greater than or equal to x1, and that's greater than or equal to both x2 and x3. And in that situation, that's the case where this output always returns x0, and this output always returns x1. And that's like one of the possible behaviors of our function. That really is like one of the fundamental pieces. I don't want to break this up any further, or else I have more pieces than necessary. And I can't make this region any bigger, because then the outputs of these two outputs might not always be x0. Like if this output is going to always be x0, it better be the case that x0 is bigger than or equal to x1 and bigger than or equal to x2. And if this is always going to be x1, that means that x1 better be bigger than or equal to x2, and it better be bigger than or equal to x3. And so that's how I get this piece here. So hopefully that makes sense. And there's another piece where this one always returns x1, and this one always returns x3. That's another region where the function is linear. And in this region, the condition is that x1 has to be bigger than or equal to both x0 and x2. So that's captured here. And also x3 has to be bigger than or equal to x2 and x1. So that's here. Okay. So it seems like to describe the possible behaviors of this function, I just have to choose for each output coordinate, does it return the value that's up to its left? Does it return the value that's right above it? Or does it return the value that's up to its right? Those are the three possibilities for every output. And it seems like I could just choose one of those possibilities for each output. So we just got to choose, one of three things for each output coordinate. Seems really easy, 3 to the something. Okay, but that's not quite right, because otherwise this would be an easy problem, and it's not. So the issue is that some of these possibilities are disallowed. There's some configurations that can't occur. For example, it would be impossible to have a region where this output returns x1 and this output returns x2, because what that would mean is, that would mean that this output looked at all three of these inputs, x0, x1, x2, and it thought that x1 was the biggest. But then on the other hand, this output looked at x1, x2, x3, and it thought that x2 was the biggest. But x1 and x2 can't both be the biggest, except in like the edge case where they're equal, but we don't have to worry about that for reasons. So because it can't be the case that x1 is bigger than x2, and it can't be the case that x2 is bigger than x1, it can't be the case that x1 is bigger than x2 and x2 is bigger than x1 at the same time. We can't have this configuration where these are both seeing the things right above them. That's not allowed. And it's also would be impossible to have them to have this crisscross idea where this one looked at x0, x1, x2, and it thought x2 was the biggest of those. And this one looked at x1, x2, x3, and it thought x1 was the biggest of those. That's impossible if they're all different things. X1 and x2 can't be bigger than each other. So this configuration also disallowed. Okay, so this adjusts our problem. What we need to do is find all the ways to assign either upper left, right above, or upper right to each output coordinate such that we never encounter these like disallowed substrings. We never have two consecutive outputs or two adjacent output coordinates that both return the thing right above them. And we can't have two adjacent output coordinates that return the thing above the other one, if that makes sense. So those two things are impossible to happen. And it turns out those are the only constraints, which is like an easy inductive proof if you want to go through it. Okay. So now we've reduced the combinatorics question to how many strings can I form from this alphabet, which I'll rewrite here. This alphabet has three things, this one, this one, this one. How many strings can I form from these three symbols which don't have these two particular disallowed substrings? And so this is like a classic dynamic programming problem, which I will try to draw here, or try to demonstrate here. So what we're going to do is split up our sequence A sub n into three baby sequences. The first one is the number of allowed strings that end in the first symbol, down to the right. The U is the number of allowed strings which end in the second symbol, and the R is the number of allowed strings which end in the third symbol. Those are the three possible kinds of strings we could have. So definitely ln plus un plus rn should be an, the number of total allowed strings. And the good news about these sequences, even though a sub n doesn't have a nice recurrence relation, which I guess I should maybe say something about. The reason why a sub n doesn't have a nice recurrence relation is that just by knowing how many strings there were of length n minus 1, it's hard to know how many strings you could make next, because how many of those strings do you think ended in the straight arrow? If you have a lot of strings that end in the straight arrow, then you can't put a straight arrow after those. So you have like not that many new strings of length n. But if very few of your strings ended in like a straight arrow or a slanty arrow, if all your strings, for example, ended in an arrow like this, then I can put anything after that. So the number of strings of length n I can produce is hard to determine just by knowing how many strings of n minus 1 there were. But for each of these individual cases, it's not too hard to determine. If I had a string, if I want to think about like how many strings of length n plus 1 there are that end in this arrow that's coming from the upper left down to the right, well, any string at all, I could just add any allowed string, I could add one of those arrows to at the end, and it would still be allowed. I can't create one of these disallowed substrings by adding this symbol onto the end. That just doesn't happen. So, so for each substring of, for each allowed string of length n, I can produce an allowed string of length n plus 1 by sticking one of these downward right-facing arrows on the end. And I guess in the case where I'm trying to create strings of length n plus 1 that are allowed and end in a straight arrow, the ways to produce those are only from the strings of length n that ended in one of the slanty arrows. Because if I had a string of length n that ended in a straight arrow, I can't insert another straight arrow after it. That would be disallowed. And so likewise for this R sequence, if I want to create strings that end in this symbol here, then my string better not have ended previously with this symbol. That would be bad. Okay. So I only produce a string of length n plus 1 that ends in the final symbol if I start with a string of length n that ends in a straight arrow, or a string of length n that ends in the arrow that comes up from the left down to the right. So those are the 3 recurrence relations for each of these baby sequences in terms of each other, right? Each of these recurrence relations is first order, but it depends on all the other baby sequences. Nevertheless, there's going to be this matrix we can construct. Like this system of equations looks pretty linear, and it is represented by a matrix. So here is that matrix. I'm going to call it A again. If I apply A to this input vector of ln, un, rn, I will get the next terms. This is just like rewriting this condition we had back here. Just rewriting that as a matrix equation.
And I have a question.
Yeah.
So would you go back to the previous slide, please?
Sure.
So our AN here, how is it constructed? So is it looking at substrings sequentially, or is it looking at all of the substrings? I'm not quite understanding exactly what AN is in terms of these other things.
So yeah, okay, so AN itself is defined to just be the number of allowed strings of length n. So for example, A sub 2 is the number of strings of length 2 built from the symbols this thing, this thing, this thing, which don't have either of these 2 substrings. And the only way to have a disallowed string of length 2 would be if the entire thing is one of those disallowed substrings. And there's 3 symbols, so there should be 9 total strings of length 2, but 2 of those are disallowed, so A2 should be 7, if that makes sense. And the idea is each of those, for AN, it's kind of the number of allowed strings of length n. Any allowed string of length n ends in one of these symbols, in exactly one of the symbols, right? So either it ends with this symbol, or it ends with this symbol, or it ends with this symbol. So L sub n is just counting how many allowed strings are there that end in this particular symbol as opposed to something else. And because every string ends in exactly one symbol, if I just add up these 3 numbers, I'm going to get the total number of allowed strings.
Okay, I see. Thank you.
Awesome.
I don't know a question also. So
Sure, yeah.
I guess it seems like naively not super obvious that just by knowing ln, un, and rn, you could figure out an. But I guess I'm guessing it's sort of non-trivial that each of those is recursively related to the n-1 value. Is that right?
So why is it that we can compute an from ln, un, and rn?
Yeah, because we have these rules that some pairings are not allowed.
I see. Yeah. Well, okay. So this equation is really just by definition of an. An is all the allowed strings of length n, and ln is the allowed strings of length n that end in this thing, and number of allowed strings that end in this thing. So it's just splitting up by cases. Each allowed string of length n has to come either from this L category, this U category, or the R category, depending on which is the last symbol in the string. That determines what category it's in. And so the recurrences for each of these categories are maybe a little non-trivial. If we, the idea here being like, well, first of all, no string. So I guess the idea here is every string lives in one of these categories. It has to either end in this, this, or this, and it can't live in two categories at once. So it lives in exactly one of these categories, and that's why the sum of these three things is an. But also, this recurrence here, I can work through it again. So like if I want to understand u sub n plus 1, this is the number of allowed strings that end in this like straight arrow. Well, how many of those are there? If I have any string of length n, any allowed string of length n, if I have an allowed string of length n and then I try to add on a straight arrow at the end, this is always fine unless the last thing here was a straight arrow. If the last thing was a straight arrow, then I'm out of luck. But if the last thing was one of the other two possibilities, then it's fine. So if I have an allowed string of length n that ends in one of the slanty things, then I could follow that by a straight thing, and that tells me that the number of strings of length n plus 1 that end in a straight thing is just is produced by like I have one string I can produce from each thing that ends in a slanty thing. Either way.
Yeah, that makes sense. Thanks.
Okay. So yeah, it is a little mystical the first time you see it, but it's we're really just building up these sequences step by step, and we're just realizing that if I had a string that was already allowed, and I add one more thing on, and this new thing didn't immediately create a disallowed substring, then I'm fine because all the rest of that string was already fine. It was already coming from an allowed substring. Okay. So this gives us our recurrence for L, U, and R, and which is represented by this matrix A. So that's just saying that here Ln plus 1 is the sum of all these three, and Un plus 1 is the sum of these two, and Rn plus 1 is the sum of these two. So nothing too crazy. And the other thing I want to say is that I can even represent An as like a matrix multiplication of this row vector by this column vector, which is just to say I'm adding up Ln, Un, and Rn, just rewritten as a matrix equation. Okay. So with those two things in mind, we have the same kind of deal as before. If I apply A once to my initial condition, I'll get like the next values of L, U, and R. And if I apply A again, I'll get the next values of L, U, and R. And if I apply A again, I'll get the next values of L, U, and R. And so if I apply A n different times, then I'll get like I'll just increment the sequence that many times. So this bit here, this 1, 1, 1, these are the values of L1, U1, and R1. Because if I have a string of length 1 and it's supposed to end in a straight arrow, there's only one possibility, likewise for L and R. And so these are the terms of L1, U1, and R1. If I apply A once, I would get L2, U2, R2, etc. So if I apply A n different times, then I'm going to get Ln, Un, or Ln plus 1, Un plus 1, and Rn plus 1. And if I add those together with this row vector, then I get little a sub n plus 1. So the total number of allowed strings should be represented by this matrix multiplication. And again, this is diagonalizable, turns out. So I just punched this into a computer. I just kind of like, I don't know, I was hoping it was diagonalizable, and by random chance it was, because like it almost always will be. So I had the computer crunch the numbers, and here's the general formula I got. It's like really the same procedure as before. I just diagonalize the matrix big A, I take the powers of the interior diagonal matrix, and then I like apply the matrices on the outside one time each, and I combine the answers, and I got this explicit closed form for this term of the sequence A sub n plus 1. Yeah, 1/7 times this complicated mess. Here, this thing was the characteristic polynomial of the matrix. So this S1, S2, and S3 are actually the eigenvalues of that matrix. And the R1, R2, R3 occur when you're trying to solve for the eigenvectors. But there's some roots of another cubic polynomial. And I guess, because the cubic equation exists, we could go write out explicit formulas for R1, R2, R3, and S1, S2, and S3, which is like tons of radicals all over the place, and it would be a really annoying mess, but we could do it. and you would get something really explicit. But this is, still precise and explicit, so that's kind of nice. And I guess I just want to conclude by what's some application of this? If you care about a particular term, like I said before, you could just take this matrix A and raise it to some big enough power with a computer and then evaluate this matrix product. So that's what I did. A1000 is a really big number, which, so in theory, this would have been hard to count by hand, right? Counting this 10 to the 351 different possibilities. But with this matrix arithmetic, pretty easy.
What
And,
library is this?
Sorry, what?
Precision?
Sorry, what? Say it again.
You use arbitrary precision for this, or is this
Yeah, it's arbitrary precision integer arithmetic. That's right.
Okay.
I did it in Mathematica, but you could use your favorite language. You could do it in Haskell, which has built-in arbitrary precision integer arithmetic, or lots of languages have support for arbitrary precision integer arithmetic. But yeah, you're gonna need many digits. But yes, you can compute whatever particular term of the sequence you want just by raising this matrix to a big power. And also, we can see from this explicit formula that if I want to take the limit as n goes to infinity of the ratio of successive terms, if I care about the growth rate of a sub n, as I increment n, how much does a sub n increase? Well, I could look at this ratio, this limit of this ratio. And in that limit, here S1 is smaller than S2 is smaller than S3. And that's going to mean that when I take the ratio and I take the limit as n goes to infinity, these terms are barely going to matter. This S1 to the n term and S2 to the n term are going to be nothing compared to the S3 to the n term, because that's just going to be much, much bigger because S3 is the biggest base. And that's going to mean that this ratio of terms is roughly just given by 1/7 R3 times S3 to the n plus 1 over 1/7 R3 times S3 to the n. And so the ratio is just going to be S3 in the limit. You can prove that rigorously, obviously, but this gives you that the growth rate the asymptotic growth rate of this sequence is roughly 2.25. So it's not the case that we're just I don't know, naively, we almost thought it's 3 to something. You just choose one of these 3 symbols for each output. But it's not quite that. So it's not that we're growing by a factor of 3 each time. There's these weird crisscrossy things that are disallowed, this substring that's disallowed. And so in the end, the growth rate is not 3, but something smaller, 2.25. So that's all I wanted to say. Just kind of a basic counting technique that's kind of fun to do. You see some problem, bunch of strings with disallowed substrings, you can solve it in this way. So that's, I don't know, I find that pretty fun. And it gives you a nice way to figure out what's the limiting ratio of things by finding the eigenvalues of these matrices. So I think it's good fun, and that's all I wanted to do. But if you really found this, super exciting and you want to do more, I got some challenge problems. So instead of, so basically very similar, if you do the same problem, but instead of having the closest 3 things get maxed together, just do it with 4 things getting maxed together in some big row of inputs. Then you have some output that's seeing all 4 of these things, etc. And there you're going to have much more. You're going to have many more possible. Your alphabet's going to have 4 symbols, and the disallowed substrings are going to be more numerous. There's going to be lots of weird disallowed configurations. And that one I think you could do by hand. The second question is find the number of 10 by 10 grids of zeros and ones where you don't have any ones that are horizontally adjacent or vertically adjacent. So for this one, the idea is to think about a 10 by 10 grid as a string of 10 columns, 10 10 by 1 columns. And those 10 columns are then each column has 2 to the 10 possibilities. That's 1,024 different symbols. And there's certain disallowed combinations. Well, some of the symbols are already disallowed because you can't have a column made of all ones that would have vertically adjacent ones. So you think about what are the possible columns, and then once you know what the possible columns are, you can think about what are the possible allowed configurations of having 2 columns next to each other, and you can form that matrix and take powers of that and plug it in. But you probably want to write a computer program to generate the matrix for you. All right. So thanks for listening to me talk.